Hello, this is section 6.1 for Calc survey, and we're going to kind of continue the discussion we had been having in chapter 5 before we dive into the chapter 6 content. So this is a good little review section for us. So we're going to analyze antiderivatives graphically and numerically. So provided the graph of the derivative here, and you're given a point on the original function. So f of 2 equals -6. Answer the following. So remember, just like in section 5.5, we talked about make sure you make a mental note. If you have a starting point on the original function, that's going to be very useful. Okay, at what value of x will the original function reach a maximum? Okay, so you've got to remember, it's so tempting to say, duh, it's right here, that's a maximum, but you have to remember you're looking at the derivative graph. All of these values indicate that the slope of the tangent line on the original function is positive. Your function is increasing this entire time until you hit the x-axis here. So even though it's tempting to say this value, you actually want to say, well, it's going to be, I said, roughly around 7.2. Okay. Estimate the maximum value of the original function. All right, so start with what you know. We know at 2, the value on the original function is -6. So from there, that's where I want to estimate the area under the derivative. So I wrote the mathematical notation for it, the definite integral from 2 to 7.2 of f prime of x dx. And this is the area under the derivative from 2 to 7.2. So again, you'd have to count the boxes. It looks like I estimated it to be about 21. So what we knew at 2 plus all of this area until we get to here, add that together and we're going to say roughly 15. So nothing new. This is what we did in chapter 5. Now, provided f of 1 equals 4 and the derivative is this, find f of 3. Okay, so you're given information. You know what you want, where you're starting, I should say, at 4. Plus, and we're trying to get the value at 3. So we're going to expand on this. We're going to do the definite integral from 1, where we know, to 3 is what we're trying to find out. And we put the derivative here, dt. Remember, we learned that the fundamental theorem of calculus says if you do the definite integral of the derivative, that will give you the change in the original function. So when you put this in your calculator, add that to 4. That's how we're getting this answer. Okay. All right, and I'm going to move me up here. So the figure below shows the rate of change of the concentration of adrenaline in micrograms per milliliter per minute in a person's body. Sketch a graph of the concentration of adrenaline in micrograms per minute in the body as a function of time in minutes. All right, so that's what I did here. So I'm going from the derivative, and I sketched a graph of our original function. So I'm going backwards. So do you remember how to do this? When you're going backwards, you want to find where it hit the x-axis. So it looks like it's right around here at 5. And we note that you go from negative to positive, so you have a minimum right there, a relative min. Then you notice that the derivative is decreasing. So I'm going to start concave down. Then here I go to increasing, so now I'm concave up this entire time while the derivative is increasing. That's where I hit my relative min. And then I end decreasing, so I'm going to end slightly concave down there. So that's kind of where I'm getting the graph. Now I put it all above the x-axis because can your adrenaline ever really truly be negative? I would doubt that. So I'm not a doctor though, but okay, and that's why I put that note over there. Pay attention to the concavity. So that was us going backwards from the derivative graph to the original function. Okay. So just another little review. Okay, and then the last example here, the figure below shows the derivative of a function of f of x. Okay, good to know. That's the note. Notice I put a big f prime right there. If f of 0 equals 3, that's important. That's a point on the original function. So notice I immediately, after I got my axes drawn, I plotted that point. That's my starting point. sketch a graph of f of x and state the coordinates of the local extrema. Okay, so my local extrema occur when you're hitting your x-axis. Notice we go from negative to positive, that's a relative min, and here we go from positive to negative, so it's a relative max. Okay, so starting with 3, starting with what you know, I'm going to subtract this value, this area. So that's where I'm getting this first. At 4, I did 3 minus 6, which gave me -3. So that's how I plotted that point. Then building from there, so -3, and now I'm going to add 10 to that to get the next ordered pair where I'll have a relative max. So that's where I'm getting this 10, 7 here. And then I'm going to do that again. So I'm going to take 7 and subtract 4 from it to get the last ordered pair at 13. And there it is. Okay, so this section is a big review section, but it's very good practice, and I highly, highly suggest you make sure you do your homework, all right? And it's really good to review how to sketch those graphs again, okay? And a really good application of from where you're starting and then working backwards using the derivative. So just a really, really good section. Make sure you do your homework and let me know if you have any questions.